This is the lecture for Module 1 of Unit 1 on intermolecular forces. Now, the question of interforces are what are the forces between molecules? In other words, what attracts molecule A to molecule B? So, in this oxygen molecule, to emphasize, I'm not emphasizing or asking about what holds these two atoms together. That's a covalent bond. You learned about those. They're very strong. However, the forces, if any, that make one oxygen atom want to stick to another oxygen oxygen molecule are in fact very weak. In general, intermolecular forces are weaker than the bonds between atoms and molecules. Okay. So the attraction here between these two oxygen molecules is not a bond in the traditional sense. It's a far weaker force. Intermolecular forces are important, however. They have a great role in physical state. At a given temperature and pressure, attractive forces are stronger in liquids than gases, and stronger in solids than in liquids. Molecules of liquids and solids are closer together than in gases. These molecules are held close together by intermolecular forces. Molecules in solids, or in crystalline form, for example, are held in one position by intermolecular forces. We should predict that as intermolecular forces get bigger, melting and boiling points increase. You have to add more heat, put more energy into a substance to melt and boil it, to overcome stronger intermolecular forces. Similarly, the enthalpy for transition increases as intermolecular forces increase. We'll look a bit at this concept a bit more in a moment. For example, the heat you have to put in to turn a mole of water from liquid to gas is quite large because the intermolecular forces involved in separating the water molecules are quite large. You have to put a lot of energy in to affect the transition. So if they're not actually bonds, what are these intermolecular forces? Well, the first kind we will consider are London, or they are sometimes called the dispersion forces. These are the result of instantaneous, allow me to correct spelling, instantaneous dipoles. For example, here are two helium atoms. Now, the notion behind London forces is that at one moment, as you know, the electrons move around in their one-s orbitals. A situation will occur in which the electrons are sort of over to the left-hand side, as it occurs in this picture. Arbitrary choice of side. As the electrons move around an atom A, an instantaneous dipole occurs. So the atom has a negative side and a positive side. Now, in general, these atoms are not polar. This instantaneous dipole does not last long. A few fractions of a second, less than thousandths of a second, if that long. But it is long enough for the positive charge here to pull on the electrons in this nearby helium atom. Electrons are attracted to the positive charge on this helium atom, or this side of this helium atom, and an induced dipole appears on the helium atom as all the electrons come over here to this side to be close to the positive charge on the first atom. Now at this point, the positive charge on this helium atom attracts the negative charge on this helium atom, and we have a London or dispersion force attracting the two. This force goes away when the instantaneous dipole disappears a few millionths or billionths of a second in the future. Similar phenomena can be observed in a collection of non-polar molecules on hydrogen atom. In hydrogen, non-polar hydrogen molecules. Instantaneous dipoles occur, and this results in a very short-lived attraction between the two hydrogen molecules. Alright, so to summarize, London forces arise because of instantaneous dipoles. They occur between all atoms and molecules, even non-polar ones. The molecules in our example are not polar molecules, but they have temporary dipoles that allow these attractions to exist. In general, London forces increase as the size of atoms or molecules increase. The bigger the atom, or the more atoms there are, the more opportunities there are for instantaneous dipoles to occur, and hence London forces increase. For example, if boiling points increases, intermolecular forces increase because you have to put more energy in to push the molecules apart. You have to put more heat energy in. So consider these halogen molecules, fluorine, chlorine, bromine, iodine. These are all non-polar materials, diatomic molecules. You all know that halogens form these diatomic molecules. Here are the boiling temperatures. For fluorine, the temperature is -188. For chlorine, -34. For bromine, 60 Celsius. Liquid bromine boils if you heat it up a bit. For iodine, you have to heat it all the way up to 184.4 Celsius to boil these molecules. And that involves a solid liquid transition in iodine that only occurs at high pressure. Iodine turns directly from a solid to a gas at normal temperatures and pressures. So even if you just consider these threes, however, observe that the boiling point increases as you go down a column of the periodic table. You must remember that the size of atoms increases going down a column of the periodic table. The larger molecules made of the larger atoms have more London forces, and hence a higher boiling point. Right, so to predict trends or magnitude of London forces, you will need to remember what you have learned about the size of atoms. Here's an exercise. Arrange the following molecules in order of increasing boiling point. Now we have C8H18, C3H8, C4H10, CH4, and C2H6 here. Now note, carbon-hydrogen bonds are typically very nonpolar. Carbon and hydrogen have very similar electronegativities. So these hydrocarbons are not polar molecules. Alright, so attempt to arrange these 5 molecules in order of increasing boiling point at this point. Stop the presentation and finalize your answer before continuing. Now here's the correct answer. The answer depends on London forces in the molecule, which increase as the size of the molecule increases. And since we are only dealing with molecules made of carbon and hydrogen, London forces increase as the number of atoms increase. So, for example, methane boils at negative 161, C2H6 at negative 88, C3H8 at negative 42. Then comes the compound with 4 carbons and the compound with 8 carbons. By the time you get up to 8 carbons, this large molecule has a pretty high boiling point, 125 Celsius. Next type of force to discuss is dipole-dipole interactions. These occur between polar molecules. ICl, for example, is a polar diatomic molecule. Iodine is the positive end and chlorine is the negative end because chlorine is the more electronegative atom. In a collection of ICl molecules, the positive end of one can be attracted to the negative end of another. In other words, this iodine on molecule Q2 feels an attraction to the chlorine here on molecule 1. Now, again, these forces are weaker than the bonds between atoms, but because these dipoles are permanent and not instantaneous, dipole-dipole attractions are stronger than dispersion forces. Now, these interactions occur only between polar molecules. So, as you will see, it is necessary to be able to discern whether or not molecules are polar. For example, a typical exercise you may be presented is which of these two molecules, and you may even be shown the shapes, has a higher boiling point. Now, the molecules are very similar in size. Here we have 4 carbon atoms. Here we have 3 carbons and an oxygen atom. Very similar in indicators of size, like molar mass. But the molecule on the right is a polar molecule. In particular, this CO bond is polar. And the dipole for the molecule, as shown, points up toward the top of the picture. Right, so for molecule A, the only attractive forces are London forces, boils at negative 12 Celsius. In the molecule on the right, in addition to similar London forces, there are dipole-dipole interactions. In the presence of these forces, stronger forces raises the boiling point or makes the boiling point a much larger 56 Celsius. Now again, to be able to predict dipole-dipole interactions, you need to be able to identify polar molecules. Final type of attractive force, or a third type of attractive force we will consider, are hydrogen bonds. These can occur in cases where a hydrogen atom is bonded to a highly electronegative atom. Now, fortunately, the number of quote-unquote highly electronegative atoms essentially boils down to 3 types: nitrogen, oxygen, and fluorine. Right, so if you're wondering if hydrogen bonds can occur, you must have a molecule in which a hydrogen is bonded to one of these 3 atoms. Now, these are actually the strongest kind of intermolecular forces. It's a type of dipole-dipole interaction. We will see how it works, considering water as our well-known example of hydrogen bonding. Right. In a water molecule, we know the oxygen has a partial negative charge because it's the most electronegative atom, and the hydrogen has a partial positive charge. So in a hydrogen bond, there is a strong interaction between the oxygen atom here and the hydrogen atom on this water molecule here. The interaction between these 2 atoms is a hydrogen bond, and the existence of these is the strongest type of intermolecular force we have looked at so far. Alright, here's another sample exercise, this sort of thing you find on a homework or a quiz. What are the strongest attractive forces in these four molecules? Again, you should stop the presentation and attempt to answer this exercise before going on. Alright, here's our solution. HF has a hydrogen bonded to fluorine, so the strongest attraction is a hydrogen bond. PCl3 is a polar molecule. If you draw a Lewis structure, it is a trigonal pyramid with phosphorus at the top. The chlorines are a little more electronegative. Phosphorus is the positive end, the three chlorines form a negative end. Since this is a polar molecule, dipole-dipole forces are the strongest forces that exist between the molecules. SF6 is a nonpolar molecule. There are no hydrogen bonds, so London forces are the strongest attractive forces. And SO2 is a polar molecule, so dipole-dipole attractions are the strongest attractions in SO2. Now note that in each of these molecules, London forces exist. Just because they are not the strongest attractive forces does not imply that they are not there. Alright, here's another exercise. Which of these two molecules has, in each pair, A and B, has a higher boiling point and a higher enthalpy of vaporization, or heat of vaporization? Pairs are CO2 versus CS2, and CH3OH versus CH3SH. Answers. In the case of A, the answer is CS2. Sulfur atoms are larger than oxygen atoms, and both CO2 and CS2 are nonpolar molecules. So London forces, depending on larger atoms, are the only things to consider in the case of these two molecules. And in second, the answer you predict is CH3OH. Unlike the other molecule, oxygens are bonded to hydrogens, which opens the possibility for the strongest type of dipole-dipole interaction, hydrogen bonds. In fact, if you look on the internet, the boiling point of CH3SH is 6 versus 64 for CH3OH. And you only have to put in 24.6 kilojoules per mole of CH3SH to vaporize it, whereas vaporizing a mole of the other species requires 35.3 kilojoules per mole, 11 more kilojoules per mole than the other molecule. The enthalpies of vaporization are again larger because the attractive forces in this molecule are larger. The three forces we have discussed at this point are the primary types of attractive forces between molecules and liquids. There are other attractive forces to consider and be familiar with. For example, species like diamond and silicon dioxide are giant covalent materials. For example, here is visualization of the structure of diamond. In diamond, every carbon atom, diamond is a pure carbon, every carbon atom is bonded to 4 other carbon atoms. 4 bonds per carbon atom, so each carbon gets its octet rule satisfied. But there are a network of carbon-carbon bonds running through the entire sample. In other words, each sample of diamond is one giant molecule made up of carbon-carbon bonds. Now we said bonds are very strong compared to the intermolecular forces we've looked at. So giant covalent materials like diamond and SiO2 have very high melting points, for example. For example, diamond melts at 3,550 C. Ionic compounds have very strong electrostatic interactions, or ionic bonds, between cations and anions in crystals. These are typically very strong, so ionic compounds have very high melting points. Sodium chloride melts at 801 C, for example, because of the strong positive and negative interactions between the positively charged cations and anions in the crystal. Metallic solids are composed of metal atoms held together by metallic bonds. These bonds are huge molecular orbitals that span across the whole solid. In other words, an electron in a metal is free to wander through its giant molecular orbital, or metallic bond, throughout the entire metal crystal. Right, well, this is the reason that metals conduct electricity. And these bonds are typically, fairly strong attractive forces. For example, magnesium melts at 650 Celsius. Iron melts at 1150 Celsius. This concludes the lecture on intermolecular forces.